It only took 12 minutes to hand out tests. You still have some class time left. So first, exam 3, I guess, is a week from today. So that would be the 5th, 6th? And the topics are everything up through Newton's second law. So we're sort of finishing that up right now. There's really only one more thing that I need to talk about, and then we're going on to the next stuff. Does anybody have any homework questions? I thought I could just answer some questions if anyone has them, and then go on to Newton's third law, the last thing I want to talk about. Okay. Yeah. Sure. Do anybody have the problems in front of them? I don't have it here. Thanks. Okay, number 11. Oh, number 11 is hard. Okay. Yes, you know, it sort of relies on on Newton's third law. So let's go over that later. Okay, so the last thing we have to talk about is Newton's third law. So I'll abbreviate this N3L, because why not? Everyone likes abbreviations. And this is the one that says, for every action, there's an equal and opposite reaction. So that's like the translated wording from Newton's, manuscript. That's not a very, it's sort of hard to take that wording and put it into mathematical terms. So we're going to think about it in sort of more of a mathy way. So we can think of it as like our version is something like this. If bodies A and B are in contact, then the force vector on A by B is equal to negative force vector on B by A. So whenever two things are in contact, they apply forces to each other that have the exact same magnitude and just the opposite direction. And that's in every case. It's always true. And it's a very useful law, especially in engineering. We'll see a couple of problems where it's useful to us. I think it's probably more useful as just like a principle. Like, for example, when I was talking about, when I first started talking about Newton's second law, I had the thing of the guy standing on the scale and said, okay, the scale isn't really measuring the weight force. It has no way to know how much force gravity is applying to a person. What it's really measuring is this contact force between the person and the scale. And I sort of glossed over the fact that all a scale can measure is the force the person applies to the scale, and I sort of treated that as like equivalent to the force that the scale was applying to the person. But Newton's third law is the way that we're able to make that jump. The magnitude of the force you apply to the scale is equal and opposite, well, is equal, since it's a magnitude, to the force the scale applies to you, you know. We will also think of it one other way. So here's how we're going to use it. For us, if body A and body B are in contact, so let's say this is body A, it's like this rolling cart, and body B is like a fish. You know, fish. That's body B. And a free body diagram of body A has the weight of the thing, so I'll say MA times G going down, and then a contact force going up. That's the normal force. And then in this instant, the cart and the fish are pushing on each other, so there'd be a pushing contact force here that I'll call R. That's a variable people use a lot. It stands for reaction. That's the reaction force from that contact. And then the free body diagram of body B, the fish, would look like there'd be weight, so MB times G. And then it looks like this fish at this instant is sort of leaping off the ground, so there'd be no contact force with the ground. But then there would be a force in the opposite direction at this one as this one, the same magnitude. And so if you solve for R on one of those, you'd know R for the other one. Nope, it would be that, so if you would get an R value that's like 50, and what this means is there would be 50 newtons pushing this way on the cart, 50 newtons pushing this way on the cart. So these two are the contact forces. And it only works for contact forces where you're just switching which body is applying to the force to which body. I've drawn this picture every time I've taught this class because I thought it was really funny back then. I remember when I first took physics, our physics teacher, Joe Delaney at Minneapolis South, drew this picture. No, it was 1989 or something, probably. I don't know. Like Mike Tyson was still, it was before he'd gone to prison. It was before he won the heavyweight championship. He was still like this up and coming guy, but he was just beating everyone up. Like everyone was talking about how great he was going to be. And my physics teacher was this like probably 55-year-old overweight nerdy guy, you know, and he's like, I wish I had a chance to fight Mike Tyson. If I fought Mike Tyson, I guarantee that I would hit him as hard as he hits me. And he drew this picture that was like, he probably worked on it like all evening getting this picture right. It was like Mike Tyson's big burly arm here. And then his like deformed face. Like all, yeah, yeah, right. Yeah, he wasn't the kind of boxer who tried to last it out for a decision. So, but if you draw, okay, so it's funny because it's uh, it's true. It's undeniably true. That's what Newton's third law says. If you drew a free body diagram of boxing glove, it would look like, or that's part of the arm. There'd be these forces here applied by the rest of the arm to this part of the arm. We don't really care about those right now. And then there'd be this pushing contact, very large force, pushing on the glove. I'll call it R. And if you do a free body diagram of the face, there'd be a pushing contact from the glove, and that force would have the exact same magnitude if you whatever the force is. The force that the glove applies to the face is exactly the same magnitude as the force the face applies to the glove. But the part that's delightfully humorous is that you will never win a boxing match by applying big forces to someone's glove with your face. So it's true. And there are some ways that this is probably one of the cases that's sort of like counterintuitive. Like, are you sure about that? So, let's think a little bit about the ways that it's intuitive and the ways it's not intuitive. Is this what our intuition says happens? In some ways it is. So here's so think about this. So this is like one of those relaxation / visualization exercises. Okay, so say you're at the park, standing you're at one of those municipal grills that they have at the park sometimes. You're cooking like Slim Jims. And you're barefoot, standing in the grass, okay? It's a beautiful day. You feel the grass on your feet. And a ball rolls over to you. You just notice this ball roll over. Okay, so you look up and there's a kid like 10 yards away. And he says, could you kick that soccer ball back over here? Okay, so it's just 10 yards. You just sort of nudge the ball back and no problem, right? Okay, could you visualize it? Okay, so now imagine the same scenario, but this ball rolls over and you look up and this kid yells from like 100 yards away, can you kick that ball back over here? Okay, so you're barefoot. There's a soccer ball there, and this kid 100 yards away wants you to kick it to him. And it occurs to you that I don't really want to do that because I'm barefoot, and it's going to hurt my foot to try to kick the ball that far, And the reason it hurts your foot to kick the ball that far is in order to get that ball to go that far, you have to apply a big force to it. And if you're going to apply a big force to the ball with your foot, the ball's going to apply that same force in the opposite direction to your foot. So in that way, you are aware that if you're trying to apply a big force to something, it's going to apply a big force to you. So that's the barefoot soccer ball. Barefoot soccer kick. But then in other ways, it's sort of it's hard to believe that this holds in every case. So also not in some ways. And so, like, imagine in a baseball game, a pro baseball game, when somebody hits a home run, imagine what happens at that contact between the bat and the ball. So when the bat's in contact with the ball, the bat's applying a huge force to the ball, a big enough force that after that force has been removed, the ball's going over 100 miles an hour, right? And the ball flies 400 feet or whatever in the air. And it never happens that the guy hits the ball and the ball stays there and the guy goes flying back, And so that's sort of like, so what's going on with that? Like, it doesn't feel right, Like, how can the ball be applying the same force to the bat that the bat applies to the ball? Well, the truth is that, yes, in that case, the ball is applying just as big a force to the bat as the bat applies to the ball. The reason the ball goes flying is, well, there are a couple of reasons. One is that the bat is heavier than the ball, and the bat is connected to a 200-pound person, and the 200-pound person is dug into the ground of the earth in spiked shoes, And so even though the same force is applied to the bat that's applied to the ball, there are a lot of reasons that the ball is accelerated a lot and the bat isn't accelerated very much. The bat just has a lot of advantages. If you're trying to avoid being accelerated, you would like to be held by a 200-pound man, And you would especially like it if that 200-pound man was wearing spiked shoes and standing on the dirt, And so that's how it works. Anybody have any questions about it's sort of a philosophical type? Well, and I wanted to say one more thing about the home run. If you like, maybe it's not such a weird thing when you think about the times that you've seen like a bat get broken in the major leagues. I remember, like, I played baseball till whenever, 8th grade or something. And like, we would break bats sometimes, but it would just be like there'd be a funny noise, and then when you tap your bat on the ground on the plate or something, it would make sort of a funny rattly noise, and you'd say, my bat's broken. In the pros, when people are throwing baseballs 100 miles an hour and people are using all the best steroids to be able to swing as fast as possible, when they break a bat, I mean, it'll explode into 5 different pieces and shards will just go flying everywhere, And that happens because they're putting gigantic forces into the ball, and the ball then is putting gigantic forces into the bat. So anybody have any? Yes. It depends. You always get to choose. You could draw, like, all the times that we've isolated a cart, if you were trying to figure out the forces that the cart was applying to the axle of its wheels, then you wouldn't isolate the whole cart. You'd isolate the the axle and the wheels or something, you know? So basically you choose what to isolate just totally based on what you're trying to calculate. There's no, there's no real definitive like free body diagram boundaries. There aren't really things, all things are made out of atoms and whatever. You can circle whatever you want. Yep. No, it cannot possibly be. Yeah, isn't that weird? It is weird. Like somebody, like, think of all the cases that it's, yeah, go home tonight and make a list of all the cases that it seems weird. Like, imagine, like, at the start of a football game, they put I guess a college football game, they put the paper thing in front of the tunnel, and all the players smash through this paper thing. Like, and you're like, yeah, that paper puts the same force on the players as the players put on that paper. But yes, it does. It's just, it doesn't take very much force to rip the paper. And so it doesn't apply very much force to the players,
You're gone past that amount of force, it's gone up.
Well, I mean, at any instant, there's a force that the player is applying to the paper, and a force equal and opposite force the paper is applying to the person. And at some point, that force breaks the paper, and then the force the player applies to the paper goes down a lot, and the force that the paper applies to the player goes down a lot. It doesn't break the players.
No. They're equal opposite reactions, but if one force is stronger, is what I'm saying, it's going to break it.
The forces are always exactly the same. It's just that force will break some things and not break other things. And once you break, if you slam into something and it breaks, then at that point, like, a lot less force is required. Yeah, I mean, there's a lot less contact force. Like, if there's a paper there and you punch through the paper, as soon as it breaks, the force drops way down almost to zero, and on the paper and on whatever you hit the paper with. Because things can withstand different amounts of force, So the paper, if you apply a force up of more than, say, 10 newtons or something, then it'll rip. And whatever's hitting it, even though 10 newtons is applied to them too, they just don't break, And that's a big part of engineering analysis, is figuring out what kind of forces different materials can withstand before they break in different ways, bend or permanently deform, or it depends what you're interested in. Any other questions about this? Okay. So let's do a couple examples and see how this works. Okay, so let's say we have 3 carts in contact. Let's say this is 1 kilogram, 2 kilograms, and let's say this is just really dense, 3 kilograms. And then there's a force of 40 newtons applied this way. And we want to know what's the force on the 2 kilogram cart by the 3 kilogram cart? Okay, well, with these kind of problems, the first thing we always do is calculate the acceleration. So we'll isolate all 3 of these together and calculate the acceleration. And there's a weight force. The total mass is 6 kilograms. So the weight force is 58.86. And then there's a contact force pushing up. I'll call that the total normal force in total. And then there's 40 newtons over there. And Newton's second law says this is in the positive x direction, so 40, 0, plus 0 in total, plus 0, negative 58.86, is equal to the mass, 6, times the acceleration. The acceleration is going to be parallel to x, so I'll just call that a0. And then the x equation says 40 is equal to 6a, so the acceleration, I think, is equal to 66 2/3. Is that right? Oh, my decimal's all wrong. 6.67. And then the acceleration vector, plug that back into the vector from Newton's second law, you get 6.670. Okay, so now we know the acceleration, and now we have to choose what to isolate. So what do you want to isolate now? Yeah, okay, so that is the natural choice, because we're trying to calculate a force on 2, and so you isolate 2 to see forces on it. But the problem is, if you isolate 2, there's going to be an unknown contact force applied by 1 and an unknown contact force applied by 3. And so those are both in the x direction. So we'll have one useful equation for 2 variables. So we can't solve that. So now what we're going to do instead is we're going to isolate the 3 kilogram, calculate, that one only has one unknown horizontal force, calculate the force on 3 by 2, and then Newton's third law says that's equal and opposite to the force on 2 by 3. Yep.
And we're doing it 2 by 3. You wouldn't do one because it's not part of what we're asking. But
right.
Theoretically, you could do one if we were asking.
Yes, that's right. And actually, another way you could do this is you could isolate, just FYI, you could isolate 1 and 2 together, and then that would let you calculate the contact force with 3 directly. I'm going to do it using Newton's third law since that's what we're talking about right now. Okay, so a free body diagram of 3. There are some problems where you're probably going to have to. So yeah, you should. And I think on the Newton's second law problems, there are a couple where it at least is really useful. Okay, so the weight is 3 times 9.81. So 29.43. And then there's a normal force, I'll call that N3. And then there's this contact force. That is the force on 3 by 2. And so Newton's second law says, okay, the way I have this drawn, that's a pushing contact force, so it has to be toward the chosen body. That's in the positive x direction, so I'm going to write that as R0. And then plus 0, negative 29.43, plus 0 N3, is equal to 3 times the acceleration vector that we just calculated before. So 3 times, I don't know, I'm going to write this as 6 2/3, so it's exact 0. And then the x equation says R is equal to 3 times 6 2/3. So so I think that's 20, right? Okay, so the force vector on the 3 by the 2 is 20 newtons pointing in the positive x direction. So in components, you could think of that as 20, 0. Or you can say it's in this direction with a magnitude of 20 newtons. And so the force vector on 2 by 3 is, first you can multiply this vector by negative 1. So negative 20, 0. Or second, it's just going to be the same magnitude of 20 newtons in the opposite direction. So you can just think of it as that direction, 20 newtons. Any questions about that? So now let's do one more thing with this. So now let's use what we just calculated to find the force on the 1 kilogram by the 2 kilogram. So now I'm going to draw a free body diagram of the 2 kilogram. There's a weight of 2 times 9.81, 19.62. There's a normal force, N2. On the right side, there's that contact force that's applied by the 3 kilogram. We just figured out that's pointing this way with a magnitude of 20. And then there's a contact force, a pushing contact applied by the 1 kilogram. So I'll call this, I don't know, F. So that's the force on the 2 by the 1. So now Newton's second law says F0 plus negative 20, 0 plus 0, negative 19.62 plus 0 N2 is equal to the mass, 2, times the acceleration, 6 2/3, 0. And so the X equation says F minus 20 is equal to 2 times 6 2/3, which is, so that says F minus 20 is equal to, I think, 13 1/3. And so, minus 20, what's going on here? So we figured that was, oh, that's not bad. Yeah, that's right. Okay. So F then is equal to 33 1/3 newtons. So the force on 2 by 1 is, there's a couple ways you can do it. Take this number and plug it into the force vector from Newton's second law. So 33 1/3, 0. Or you can say it as a magnitude of 33 1/3 pointed to the right. And so now that we know this, the force on 1 I2 is, you can think of it as multiplying negative 1 times the force on 2 by 1. So negative 33 1/3, 0. Or same magnitude, opposite direction. Any questions about that? Okay, so
number 2 is R value going to the right and to the left, so that resistance on either side is applying the 33 on one side and the number on the other is 40.
Okay, so for that one, we're isolating the middle one, so that 40 isn't being applied, but what is being applied is the force. The first thing we calculated was the force on the 2 by the 3. So that was a 20 Newton force going this way. So when we isolated the 2, we had a force that we knew, 20 newtons, we knew that from the part before, and then the unknown force from the one on the left. And we calculated that force. Now, you know, if instead of doing all that, yeah, I mean, I guess you can think of it as like all of that applied force is 40 newtons pushing it this way. And so a little bit, this is sort of like a loose way to think about it, but a little bit of that force is required to accelerate each one of these. So the contact force is going to drop down each one to the, as you move to the left. Sorry, to the right. So this is 40 here. This is 33 here. This is 20 here. It would keep getting smaller and smaller as you, if you had 20 carts or whatever. It's just sort of like the cost, because you take off the cost of accelerating each one of these carts as you go. Yeah, that's sort of I mean, I guess it's the acceleration times the mass is what's left over. Here. And if instead of going through all that, the problem had just in the first case, just asked what the force is that's applied to the 1 kilogram by the 2 kilogram. We wouldn't have done that roundabout thing. We would have, after we calculated the acceleration, we would have just isolated the 1 kilogram part. And if we would have done that, just directly going to the answer, we would have gotten the same thing, the same answer for the force on the 1 by the 2. So it all these things, there's, using Newton's third law, there's always multiple ways to solve these problems. But no matter how you do it, you get the same thing. Okay, let's do that one crazy one. That one, let's do number 11. Thanks. This is not like anything that I would ever put on a test in a million years. But I mean, I think it's useful for sort of thinking through the concepts, But okay. So this is Newton's second law, number 11. So there's a 10 kilogram box sitting on top of a 25 kilogram box. And that's on a floor. And then they're connected to each other by a cable. That goes over this pulley. At the instant shown here, first it gives coefficients of friction. So at this contact, the coefficient of friction is 0.1. And at this contact, the coefficient of friction is 0.2. And at this instant, the top block is sliding to the left. If that cable can't stretch, then if this one's sliding to the left, this one has to be sliding to the right. And whatever the acceleration is of this one has to be the same magnitude, opposite direction of the acceleration of the one on the bottom. So I think we use that in this problem. So let's just, since we want to calculate the acceleration of the 10 kilogram, I think the thought process would be, let's try isolating that and see what we can get. And then maybe we'll have to do something else too. So free body diagram for the 10 kilogram. There's a weight force down of 98.1 newtons. And then there's a pushing force from the 25 kilogram box. I'll call that N1. And then the top box is sliding to the left, so the friction force has to be to the right. So this will be the coefficient of friction between those two, 0.1 times N1. Any questions about that yet? So Newton's second law says 0, negative 98.1 plus 0 N1 plus 0.1 N1 0 is equal to the mass times the acceleration, and this thing can only slide parallel to the x-axis, so I'll write it like that. Yep, question? Yes, yeah, we do. Yes. I just totally blanked on that. Thank you. So yeah, we also need the tension. Thank you. Tension is always positive and it always acts away from the body you're isolating. And the key thing, a key thing to notice here is that these two forces together, this pushing force and this friction force, those are the force on the 10 by the 25. Like if you add those two up, that's the total force applied to the 10 kilogram by the 25 kilogram. And so we're going to use Newton's third law on those. So the x equation says N1 plus t is equal to 10a. The y equation says negative 98.1 plus n1 is equal to 0. So with these friction problems, we always use the y equation to solve for the normal force and then plug that into the x equation. So this one says n1 is equal to 98.1. And so then use that in the x equation. And it says 0.1 times 98.1, so 9.81. That's just 0.1 times the normal. Plus t is equal to 10a. And now we're stuck. We can't do any more with this. So we're just, all we can do is hope that we can come up with a system of equations that'll let us solve. We can't do anything with this because it's a single equation with two variables. Okay, so there's no solution to that yet. We need another equation that deals with those two variables. So now we'll isolate the 25 kilogram box. There's a weight force. So 25 times 9.81 is 245.25, I think. And then there's the cable force. So don't forget that this time. And at the bottom, we have the force from the ground. That's a normal force that I'll call N2. And then there's a friction force. Which way is the bottom box sliding? To the right. So the friction force has to be to the left. And for this one, the coefficient is 0.2, so this will be 0.2 N2. And then the forces from the top. Now we know what these are. Well, we don't know what they are numerically yet, but we know that, oh, we do know what they are numerically. Because we know what N1 is, and we know that the force on the 25 by the 10 is just equal and opposite to this. Okay. So that means we have a force coming down with a magnitude of 98.1. Because in the free body diagram of the 10 kilogram, we have it acting up. And then since in the 10 kilogram, we have the 0.1 N1 acting to the left, over here it has to be acting to the right. So that's 9.81. Any questions about that? So then Newton's second law says 0, negative 245.25 plus T0 plus 0 N2 plus negative 0.2 N2 0 plus 0, negative 98.1 plus negative 9.81, 0. And that's all the forces, I think. Okay. Is equal to the mass, 25. And now is where we have to recognize that the acceleration would be equal and opposite to the acceleration of the other one. So this is going to be an acceleration of negative a0. Can you imagine if I put this on a test? That'd be super uncool. Okay, so then the x equation says t minus 0.2 n2 minus 9.81 is equal to negative 25a. And the y equation says negative 245.25 plus n2 minus 98.1 is equal to 0. So just like always, we can use the y equation to calculate n2. So that's 343.35. And then combine that with the x equation, and you get t is equal to What's 0.2 times 343.35? 6.86, 68.67. Cool. Okay, so T minus 68.67 minus 9.81 is equal to negative 25A. So T minus 78.48 is equal to negative 25A. And that's our second equation for the same two variables. Now you solve that system. You know, so now you have two equations for two variables. The first one says T minus 10A is equal to negative 9.81. And the second one says T plus 25A is equal to positive 78.48. So negative 35A is equal to negative 88.29. So what's 88.29 divided by 35? 2.523 meters per second squared. And that's this way. So is this system speeding up or slowing down? I think, so this is the acceleration of the 10 kilogram, the acceleration of the one on top. And I think the problem said it was at that instant moving to the left, so it's slowing down. I think this is one of those problems that's like no individual step is really like, well, some of the individual steps are sort of subtle too, but it's really just putting it all together at the same time that makes this like really, really hard to get through, you know. Okay, let's stop. So we have, that's the end of this material. If you have any questions about homework, on Wednesday, I'd be happy to start by answering any of those, and then we'll just go on to new stuff that's not going to be on the test. Okay.